Hi everyone, I'm Kai Ping. I'm happy to share our work exploiting negative samples, a catalyst for cohort discovery in healthcare analytics. Healthcare analytics is to perform analytics such as diagnoses and prognoses, leveraging diverse healthcare data. Let's take a diagnosis or prognosis problem of predicting whether a patient will develop a certain disease as an example, which is a binary classification. We note that positive samples, patients who develop the disease, are defined according to rigorous medical criteria based on medical theories and experience. However, negative samples are defined in an unrestricted manner, generally as the complementary set of the positive samples. In a nutshell, positive samples are well defined and bounded, whereas negative samples are diverse and open-ended, leading to an inherent fundamental asymmetry in healthcare analytics. Despite such fundamental asymmetry, previous research has not well addressed the role of negative samples. However, it is crucial to investigate negative samples to comprehensively study the disease. While the disease may not have developed in these samples, some may exhibit similar symptoms or develop related conditions, like comorbidity or complications. In this sense, they could reveal future positives, pathological correlations, or similar conditions. And this reciprocal relationship between negative and positive samples could contribute to defining positive samples in theoretical medical research. To this end, we aim to bridge the research gap caused by the asymmetry between positive and negative samples and propose to achieve cohort discovery among negative samples. Our innovative approach mainly consists of three components. First, we propose to quantify each negative sample's contribution to the prediction task using data Shapley values, and then construct the negative sample Shapley field to depict the distribution of all negative samples. However, we note that this originally constructed negative sample Shapley field is suboptimal for cohort discovery among negative samples due to its anisotropy in data Shapley values. To overcome this issue, we transform the original field by manifold learning while preserving the original data structure information and ensuring that changes in data Shapley values are isotropic in all orientations. Finally, in the transformed manifold space, we identify densely connected clusters among the negative samples with high data Shapley values through db-scan. These clusters help identify our target cohorts, exhibiting similar medical characteristics with high data Shapley values. We adopt a distinct perspective by focusing on negative samples and emphasizing the significance of cohort discovery among them. Different from existing work, we conduct an innovative Shapley-based exploration of interrelationships between samples, extending beyond traditional feature-based similarity methods. Our proposal asserts that valuable cohorts should exhibit similar distributions with high data Shapley values. For the experimental evaluation, we focus on cohort discovery for acute kidney injury prediction on real-world electronic medical records, EMR for short. This subfigure displays the data Shapley value histogram among all the negative samples, which can be well fitted by a Gaussian mixture model. Consisting of three distinct and interesting components, we focus on the third component, that is, 40% samples with high data Shapley values for identifying cohorts. The distribution of all negative samples, in terms of their data Shapley values in the manifold space, is presented in this subfigure. By performing db-scan on the 40% samples with high data Shapley values, we identify 7 distinct cohorts of interest that are visually displayed using TSNE plots in this subfigure. We dive into the representative cohorts discovered by our approach, namely Cohort 2 as the inflammatory cohort, Cohort 4 as the hepatic and hematological disorders cohort, and Cohort 6 as the respiratory failure and metabolic acidosis cohort. After being clinically validated by medical professionals, our derived cohort discovery results confirm the correctness of the outcomes and the medical utility of our approach. We further demonstrate the ability of our approach to decompose high-data Shapley value samples into distinct, medically relevant cohorts. This figure presents the data Shapley value histogram of our identified cohorts, with the upper part aligned with Figure 2a, but color-coded by cohort proportion. The lower part shows each cohort's data Shapley value distribution. We note that 7 cohorts effectively partition Figure 2a's third component into Gaussian distributions, implying consistent data Shapley values within each cohort. We refer the interested audience to the full paper for more comprehensive experimental results, including effectiveness validation of each component, ablation study, comparisons with diverse baselines, and cohort discovery analysis on the MIMIC-3 benchmark dataset. To summarize, we bridge the research gap caused by the asymmetry between positive and negative samples in healthcare analytics by exploring negative samples for cohort discovery. We propose an innovative approach for effective cohort discovery, constructing the negative sample Shapley field, transforming the field by manifold learning with structure preservation and isotropy constraint, and discovering cohorts in the manifold space via DB-scan. We evaluate the effectiveness of our approach using the EMR data from National University Hospital in Singapore. The results demonstrate the effectiveness of our proposal, and the medical insights derived from our discovered cohorts are validated by clinicians, underscoring our approach's substantial medical value. Thanks for watching.